That's the result that we just calculated using the matrix mechanics, and we have to show the same result is obtained using path integral. So let us do the path integral computation now. So d2 dt2 plus omega square acting on f time ordered product x hat t x hat t prime I is equal to dxi to f e to the power I by h bar s I f of x, then d2 dt2 plus omega square acting on xt prime. This is the path integral statement, and now you can use a trick to calculate this. This is nothing but the equation of motion, and therefore it should be same as the variation of the action. So show that del s del x of t is equal to minus m times d2 dt2 plus omega square x of t. Now this is a functional derivative. Let us assume this result, and we can discuss functional derivatives separately if needed. So therefore, your expression is minus 1 over m integral dxi to f to the power I by h bar s I f x delta s delta xt, and this can be if, because SIF, this IF refers to the limits in the time integration. Since you are doing derivative of xt at time t, which is between I and f, it is the same times xt prime. Now you can write the same thing as minus I h bar over m integral dx I to f del xt of e to the power I by h bar s I f of x. So what I've done is combined these two to write this, because derivative of this exponential is exponential times I by h bar del s del x, right? So that I by h bar will cancel with this. This is plus sign because yeah, so if it acts on this, it will bring down an I by h bar times del s del x, and I by h bar multiplied by I h bar should give you minus. So I need a plus here. Right now, now you want to do an integration by parts. Now to proceed further, we shall assume the following result, that integral dxi to f del xt of e to the power I by h bar s I f x times x t prime is equal to 0. This is analogous to the usual equation integral dx ddx of some function fx is equal to 0, provided this vanishes at infinity, where the boundary is, or at boundary. Now, this statement is not very straightforward. In the usual ordinary integral, we know that it is it gives a boundary contribution. Say whatever the boundary is, you pick the boundary contribution, and if f is 0 at the boundary, then the result vanishes. So if you are integrating between minus infinity and plus infinity in the full range, then f plus infinity and minus infinity must be 0. So now there are two types of complications here. First of all, what is the meaning of boundary here in this case, in this functional integral or path integral? And these effects has to, if we think the boundary is some kind of infinity, minus infinity, plus infinity, some kind of infinity, then we see that here fx, that whatever we have corresponding to fx, does not really satisfy that condition, because x at the boundary must be very large, and it has a phase multiplying, and therefore it does not vanish. Now, so these two questions have to be answered. The first question can be answered in the following way, that what is the boundary of this path integral? So one is integrating about over the paths which has a fixed initial and final condition. I was calling that as boundary condition for each path to be satisfied. Now, whatever boundary we are talking about is separate from that. It is that given this fixed point initial and final, what would be the so for example, there is a classical path between initial and final. So let me draw some cartoon here again. So this is initial and this is final. Okay, so this is this. So this is initial, and then there is a final point. And suppose there is a classical path. This is about this path. So you may assume that the path integral is centered around. It is like x equal to 0 for this in this example, and it is like the path integral is centered around this path. So then you should go to the extreme paths around that center, like minus infinity and plus infinity with respect to 0. So it is that boundary in the path space, or the curly F that I mentioned earlier. So this is like small deviation from the path. This is large deviation. So the highest deviation, maximum deviation that you can imagine. Now, you could, if this is your classical path, say, so that is say x lower bar, then you can always write, you could always write x of t as x lower bar of t plus y of t, and then you think of the average position of y to be 0, identically 0 function. So y vanishes. Okay, so you take, so x, so both these two and the classical path same satisfies same boundary condition, meaning both x t and x lower bar t at t equals ti is xi. Similarly, both xt and x lower bar t at t equals tf is xf. Therefore, y ti is equal to y tf is equal to 0. So y boundary condition vanishes, and therefore you could write, you could plot y of t against t. Sorry. You could plot y against t. So this is t, this is tf, and suppose this is ti, and this is y of t. So y of t is all possible functions. Yeah, y of t is all possible functions which starts from 0, ends at 0, and so these are all possible paths. Now in that you have to consider the boundary in this case of the path integral corresponds to, so you could write the dx is same as dy, because x lower bar is a fixed path, and therefore the entire calculation becomes a y path integral instead of an x path integral, and therefore we are talking about now y boundary of the y path integral, and the point is that boundary of y path integral would be like a very largely deviated path satisfying the same boundary condition, something like that. Now, this is not a very well defined concept. You have to do up or take an operational definition that I earlier referred to, where you are discretizing time in time slices, and then divide the entire path integral as a product of infinite number of a large number of integrals, and you use this concept, the usual concept for each segment of or each slice, time slice. That is how you could do. That is how you could define this, where every mode, every intermediate time mode, the boundary of y will be minus infinity and plus infinity. So the path here it is 0, but for the next path the variation is from minus infinity to plus infinity. And that is how you could view this, and then calculate and then take large end limit. So this is roughly the answer for the first problem, first question. So that is a question of what is the boundary. So the number one question was what is the boundary for path integral? And number two, other question is the analog of A, analog of fx, which is this e to the power I by h bar s times x, does not vanish at boundary, rather the quantity is most likely wildly fluctuating near the boundary. What I mean is that having answered what the boundary is like, now let's look at this integrand. I mean, integrand being derivative of the fx, where fx is this e to the power I by h bar s times x. Since x is linear, it is certainly increasing towards the boundary, but depending what kind of action you take, depending on what kind of action you take, for very largely deviated paths, this may be very wildly fluctuating phase, and therefore this quantity is extremely wildly oscillating near the boundary, and that is certainly not zero, and we need to have a better we need to be better equipped to calculate such things. Now we will do that later on. It's called euclideanization of path integral. We will explain that in detail later, and we will see that there is a way of doing an analytic continuation, which in the analytically continued expressions for path integrals are computable, and there you can show that it does vanish at the boundary, at large fluctuation, largely deviated paths. So that concept will be, so in all our calculations in the real path integral, all the calculations will suffer from this difficulty of wildly fluctuating phases, and we are actually not in a position to do the calculations because these are wildly oscillatory. What we have to do is to do that analytic continuation, which is called euclideanization, and it is in that framework that we can do the calculations, and I'm not in a position to explain it now. We will do that, so we will just simply assume this result for now. Now, given this discussion, what we have is that now this is same as a derivative on this times x plus this times derivative on this. So we have derivative on the exponential times x. So this is negative of exponential times derivative on this. So that the result is minus I h bar over m integral dx I to f e to the power I over h bar is I f x and del x t prime del x t, and that according to the functional derivative rule for functional derivative is delta Dirac delta. So minus I h bar over m delta t minus t prime integral dx I to f e to the I by h bar s I f of x, which is same as minus I by h bar over m delta t minus t prime f over I. That's the result that we expect. We calculated in the Schrodinger theory, and now we got the same result using path integral. Now that will be the end of discussion now, except that I have to explain a couple of things. One is that distribution law, and the other is this result. Is this result in functional derivative? So I think I would rather do it in an additional note. So so distribution law and functional derivatives. So so look at additional note number 2 for distribution law. law plus functional derivative. Okay, I'll end this video here now.